Hello, in this video, we're covering DeMorgan's laws and deduction, logical deduction, two sections in the notes. So DeMorgan's laws are used for negating compound statements. So here's an example. To be a president, you have to both be born in the US and be at least 35 years old, right? Two conditions. Be born in the US and be 35 years old. So let's start breaking this up with some symbols. So born in the US, call that P, 35 years old, Q. So to be president, you have to be P and Q, right? So what's the minimum set of conditions that would disqualify someone from being the president? In other words, what is something that would negate that? So we could say you're not born in the US, or you're less than 35 years old. If either of those hold, you're not qualified to be president, right? So notice the negation of this. Not born in the US is not P, or not less than 35 years is not Q. So isn't that interesting? To negate the end statement, the end, I'm going to highlight this here. The end, to apply the negation, in a sense, we're distributing the negation to these two statements. The end becomes an or. Okay, so let's look at another one. So for Valentine's Day, you did not get your sweetie flowers or candy. Uh-oh, you're in trouble. You did not get your sweetie flowers or candy. There's two conditions here. Not get flowers and not get candy. So in this case, really what we're saying, like the implication of this is you didn't do either, right? You're in trouble. So you not got flowers and you did not get candy. All right. So that's actually what we're saying here. So in this case, if we're going to call P got flowers, Q got candy. So P or Q, you're good, P or Q. But if you negate that, that's the same thing as saying not P and not Q. Okay. So yeah, like think about how we're negating these statements. What about this one? I do not like carrots or zucchini. How would I write that? If C is I like carrots and Z is I like zucchini, this is like saying not C and not Z. He's saying not carrots or zucchini, which is the same thing as not carrots and not zucchini. You see how if we distribute that negation symbol, it changes the or to an and. All right. So it looks like the correct answer to the equivalence is those two are equivalent, right? Yeah. Okay. So here's the summary of all that. To negate not P and Q, it's not P or not Q. And to negate not P or Q, it's not P and not Q. The and or flips. All right. So we'll apply that in the homework, but I'm going to continue to the next section, deductive arguments. There's really two kinds of arguments that people make. Inductive is you take a bunch of little information and you make a bigger conclusion. Deductive is you take a big bunch of information and you make like one or two conclusions. Lots of information and you distill it. So we're going to work on some deductive arguments. And one way to look at deductive arguments is using what's called a Euler diagram, an Euler diagram. That's how you say his name, Euler, Leonhard Euler. He's a mathematician. And this is basically the same thing as a Venn diagram, if you're familiar with Venn diagrams. So let's look at this statement. All cats are mammals. Okay. So this is the same thing as saying if here are all my cats, cats are included in mammals. All cats are mammals, right? They're a subset of the mammals. Okay. So if a tiger is an element of the cats, here's a tiger. Well, notice the tiger is also an element of the mammals. So a tiger is a mammal. And that's valid. A tiger is a mammal, right? Or what about no cows are purple? How can we use that information? You could say, okay, here's the cows. They're here. And here are the things that are purple. None of the cows are purple. I'll say things that are purple. Right? Okay, and this encompasses lots of things. But if I say Fido is out here, he's not a cow, therefore Fido is purple. That could be true. Maybe Fido's in the purple set, but maybe he's not. He could be outside the purple set. So this is invalid. Right, you can see that Fido could be something else. So you see how we can use sets, Venn diagrams that either overlap or don't in various ways to think about this. It's like a logical tool. Okay, so here's another example. If a person is on this reality show, they must be self-absorbed. Okay, so here's the way to draw that picture. Here we got the reality show, or people on the reality show. Okay, if they're on the reality show, then they must be part of the set of self-absorbed people. Okay, so Laura is not in the reality show people. So Laura is somewhere outside. She could be in the set of self-absorbed people, or she could be outside the set of self-absorbed people. We don't know. But, oh wait, she's not self-absorbed. I have to correct that. If she's not self-absorbed, she's outside of this whole set. Okay, so here's Laura outside the set. Now, since she's not part of the self-absorbed people, there's no way she could also be on the reality show. So this is valid. She cannot be on the reality show. All right, let's do one more and then the rest I'll leave for a quiz, okay? So if you are a triathlete, then you have outstanding endurance, okay? Think about how we could set this diagram up. So triathletes, and then they must, if you're a triathlete, then you must be also part of the people that have outstanding endurance. Okay. So LeBron James is not a triathlete. Okay. LeBron, he's not in here. He's not in the triathletes, but he could be here or he could be here. So now what's our conclusion? He does not have outstanding endurance. That's not valid because he could still have outstanding endurance and not be a triathlete. He also might not. I don't know if he's still active, but this logic is not valid. The set of triathletes is contained within those with outstanding endurance, but may not be the same thing, right? There could be people who are not triathletes that have outstanding endurance. So another way to think about these examples is, can you come up with a counterexample and use the tools you have to think about it logically? All right, so I'll put these on the quiz. And and we'll see you. Oh, one more tool for evaluating truth table, deductive arguments is with truth tables. Okay, so we can, using the tools from the previous quiz, we could like break down our statement into like logically connected statements and then join them together. So I'll look at these examples here. I'll do 2 of them for you guys and then 2 on the quiz. So here's our statement. We're going to see if this is valid or not. If you brought bread, then you went to the store. Okay. This means if you brought bread, let's say B is bought bread. And then S is went to store. Okay, we're assuming B implies S is true. Like this statement is true. All right, then B is true. So let's break it up. The truth table for B and S, true, true, false, false, true, false, true, false. B implies S is true, false, true, true. So that's true. We know this holds. And B is true also. And so now, if B implies S and B is true, which one are both of those true? This one's true, this one's false, this one's false, this one's false. Okay, so this is the only case that could happen. So the conclusion, you went to the store, S also must hold. It also fits in the possible cases. It's the only possible case. Okay, so this is valid. The conclusion is a valid statement. Okay, I'll do one more with you guys. So, part of what I'm showing you is just tools for breaking down arguments and think about them. You might be able to reason through these without any of the tools that I'm providing, but sometimes when statements get complicated enough, it's easy to get tricked. And this is what people can try to, a salesman will certainly try to trick you with their logic. So if you can find the holes in it, then you are going to make better decisions. And that's kind of the whole point of why I'm choosing these topics is they can help us make better decisions. So if I have a shovel, then I can dig a hole. Okay, so let's call S shovel. I have a shovel. D is dig a hole, can dig a hole. So we're going to assume S implies D is true. Okay. And then we're going to say dug a hole, D is true. Okay, so let's make this the truth table for it. S, D, S implies D. So true, true, false, false. Okay, so we know S implies D is true and D is true. So where is S implies D? I need to erase something here. And D, where are both these true? So this case is true. This case is false. This case is true. This case is false. You know, these are the only ones where both hold. Okay. So either one of these cases can hold. This case or this case. Hold. One of these two cases. Okay. So conclusion, I had a shovel. is that always true? Use some highlighting here. Either this is true or this is true. Is it the case that in both those you had a shovel? And so actually, though you had a shovel in one of the cases you did not have a shovel. So it's possible to have dug a hole in some other way. I could have had a stick and dug a hole with it. And this sequence of truth like truth evaluations shows that it could be invalid. There is a case where it's invalid here. The conclusion is invalid in this statement. All right. Okay, so get with these and see how you can model them. If you have another way of thinking about it, besides truth tables or Venn diagrams, some of these you can think about directly using just the logical sequence of like joining these statements together. But hopefully this gives you some tools for evaluating the rest of these. All right, so we'll see you in the very last video next.